Here we go. We're going to walk through the fall 2018 final for MA266 from questions 9 all the way through 20. I think we skipped 13 along the way, but other than that, we are doing everything. The general solution to this homogeneous differential equation is c1 x squared plus c2 x squared ln x, and we're applying variation of parameters to find the particular solution to this non-homogeneous differential equation. Right off the bat, we need to get things into a form where y double prime is by itself. It has no x component or no factor multiplied by it. So let's divide everything by x squared. And really, we care about what our right side is divided by x squared, because the equation that we're about to use for the variation of parameters is y of t, well, this is yp of t, is equal to negative y1 of t times the integral of y2 of t times f of t over the Wronskian of our two fundamental solutions, dt plus y2 of t times the integral of y1 of t times f of t over the Wronskian dt. And in order for us to have a correct f of t to plug in, we need y double prime to be to have a coefficient of 1. So we see here that f of t in our case is 5 ln x. We already know that y1 of t and y2 of t are given as the solutions to the homogeneous differential equation. So that will be x squared and x squared ln x, x squared ln x, and then the Wronskian is the last thing we need to find, and that's going to be the determinant of x squared, 2x, x squared, ln x, and then down here we'll have 2x ln x plus x, where this Wronskian is just our two solutions on top, y1 and y2, and then their first derivatives below. And we're taking this determinant. This will be 2x cubed ln x plus x cubed minus 2x cubed ln x. And so this is just x cubed. I'll put that up here. Our Wronskian is x cubed. So I get rid of all of this, and we can fill in all of our values into our big equation here. So our y1s are x squareds, our Wronskians are x cubes, our f of t's is 5 ln x, 5 ln x, and over here 5 ln x, and then our y2s are x squared ln x. So here we have x squared, and then I'll just square our ln x, and x squared ln x. Okay, have everything set up. Let's simplify. In our first integrand, we will get x on the bottom, so we're actually integrating this guy right here, and then over here, yet again, we are getting 5 ln x over x. Okay, so and at this point we're actually done, because I just realized what they're asking for is the function multiplied by x squared here and the function multiplied by x squared ln x. And even nicer than that, they want u1 prime and u2 prime. And the derivatives of these is just going to be what is in this integrand, although we do have to factor in this negative 1. So we have negative 5 ln x squared over x, and 5 ln x over x. 9 is C. 10, we have a spring mass system set in motion determined by this initial value problem, we need to find the amplitude of the motion of this spring. So this is an undamped, unforced oscillation here, so we can just take our characteristic equation, r squared plus 49 is equal to 0, r is equal to plus or minus 7i, and so UC, or our characteristic equation, which actually is just u of t, we have no particular solution to add on here, C1 cosine 7t plus C2 sine 7t. And let's find u prime of t. That will be negative 7c1 sine 7t plus 7c2, not sine, cosine 7t. And plugging in u at 0, we see that 3 is equal to c1. And down here for u prime, we see that u prime of 0 is equal to negative 7, which is equal to 7c1. So c1, sorry, that's c2. c2 is equal to negative 1. And we are effectively done here. They're looking for the amplitude of this motion. If we go back up to our equation for u of t and replace these here, we know that the coefficient on sine and cosine we can call a and b, and c, the amplitude of motion, is the square root of a squared plus b squared, which in this case is 3 squared plus 1 squared, so root 10. So 10 is A. 11, let's find the general solution of this fourth order homogeneous differential equation. We can pull out our characteristic equation, that's r to the fourth plus 5r squared minus 36 is equal to 0. This factors to r squared plus 9, r squared minus 4, if I'm correct. Yep, that should be good, is equal to 0, so r is equal to, solving each of these individually, plus or minus 3i, and r is equal to plus or minus 2. So our equation y of t will be in the form c1 e to the 2t plus c2 e to the negative 2t, using our constant real values for r, and then with this imaginary conjugate pair here, we'll have plus c3 cosine 3t plus c4 sine 3t. And if we just look through our options here, I'm liking D. Just going to make sure that our other options are, yeah, definitely wrong. Okay, 11 is D. 12, which of the following functions is a correct form of a particular solution to this equation here? So really what they're asking us is, what would our guess be for a particular solution if we were solving using undetermined coefficients? So what we have to figure out is what's the characteristic equation, so that we can then determine what the characteristic solution yc will be made up of, so that we don't have any overlap here. Because what we would like to say is that our solution would be in the form a e to the t plus a, and not a, bt plus c e to the negative t plus d cosine t. That would, and plus e sine t, because they always come in a pair. That's what we'd like to be able to do, but there's a pretty good chance that that is not going to be applicable. Let's pull out our characteristic equation. That's r to the fourth is equal to 1, or r to the fourth minus 1 is equal to 0. This will factor to plus or minus 1 and plus or minus I. Yeah, that checks out. And what this means is that this I component will give us a sine and a cosine multiplied by some constant value, and it will also give us an e to the, so I'll write this out. This will give us an a c1 cosine t plus c2 sine t. This will give us a c1 e to the t plus c2 e to the negative t. And for each term here, out of these four that is matched by one that we have in our guess, we have to multiply that corresponding guess by enough t's so that we no longer overlap. So this a e to the t has to be multiplied by t. This c e to the negative t term has to all be multiplied by t. And this d cosine t and e sine t all have to be multiplied again by t. So E is our correct answer for 12. Okay, skipping 13. 14, we are trying to find the inverse Laplace transform of this thing right here. And I copied our handy table over here so that we can reference it. Let's split this up a little bit. So f of t is equal to the inverse Laplace transform of 4e to the negative alpha, I'm using alpha, multiplied by 1 over alpha squared plus 2 alpha minus 3. Will that factor? Well, yeah, that will. That'll be alpha plus 3 alpha minus 1. And if we can successfully do some partial fractions on this expression right here and split it up into a term over alpha plus 3 and a term over alpha minus 1, we can use our inverse Laplace transform rule right here, this little pair, to solve everything relatively easily. So let's solve this. We have 1 over alpha plus 3 times alpha minus 1. That's equal to sum a over alpha plus 3 plus sum b over alpha minus 1. Multiplying our denominator up from here to everything, we see that a alpha minus a plus b alpha plus 3b is equal to 1. So negative a plus 3b is equal to 1, and a is equal to negative b. Changing this a into a negative b, this will become 4b, so b is equal to 1 over 4. And down here, a is equal to negative 1 over 4. So running with this, we're now dealing with negative 1 over 4 and 1 over 4. And we know that all we're doing, I'm going to get rid of this, all that we are doing when we take the Laplace transform, or the inverse Laplace transform of some function here, well, this is the Laplace transformed version of some function times e to the negative cs, we are just going to take the normal Laplace transform, the normal inverse Laplace transform, but we will replace all of the t's that we get with negative t's. So let's see if we can pull that off. I'm going to factor a 1/4 and this 4 out, so we are left with the Laplace transform of e to the the inverse Laplace transform of e to the negative alpha times negative 1 times 1 over alpha plus 3 plus e to the negative alpha times 1 over alpha minus 1. We know that the Laplace transform of the inverse Laplace transform of 1 over s minus a is e to the at, and applying that and the rest of this rule over here, these individual halves will become, well, our first one will be negative u1 of t, the unit step function beginning at 1, times e to the negative 3, and then where we would put a t, we have to replace that with t minus c, the value that's multiplied by negative alpha here. And then secondly, we will get plus u1 of t times e to the positive 1 t minus 1. And this we're saying is equal to f of t, and we are looking for f of 3. So if we plug 3 into all of this, we know that the unit step function for some c value is equal to 0 below that c value from t is equal to 0 up to c, but then at c it will jump to exactly 1. So here, because we're trying to find f of 3, both of these u1s of t will be active, so we will have negative e to the negative 3 minus 1 is 2 times 3 is negative 6 plus e to the 3 minus 1, so 2. And that gives us c for 14. I think that's the first time I've actually gone through that problem the whole way. It's pretty satisfying, gotta say. Okay, question, we're bringing question 14 along with us. Okay, question 15, get rid of this. The solution of this initial value problem is given by what? Actually, we're going to need more room than just this. So we know that for solving these initial value problems, that the Laplace transform of y double prime is equal to alpha squared y of alpha minus alpha y of 0 minus y prime of 0. We know that the Laplace transform of y prime is equal to alpha y of alpha minus y of 0, and we know that the Laplace transform of y is equal to y of alpha. And so applying all of these things, we should be able to put this into a form that we can eventually take the inverse Laplace transform of to get back to the t world from the alpha world. So let's set this up. We have a y double prime that will Laplace transform to alpha squared y of alpha minus alpha y of 0. They tell us that y of 0 is a, so alpha a minus y prime of 0, so that's minus b. And then we have 4y, which will transform to plus 4y alpha. And then the Laplace transform of g of t, I will just write as, not like that, capital G of alpha, because g is some arbitrary function of t, and just like how the Laplace transform of y of t is written sometimes as capital Y of s, or in this case alpha, whatever. I'm confusing myself with my own variables. We're going to use a capital here to denote that as well. Okay, let's add a b over to this side, plus b. Additionally, we're going to add our alpha a to this side, plus alpha a, and factor our left side, and we'll be left with y alpha times the quantity alpha squared plus 4, which can then be divided by everything on the other side. So we have divided by alpha squared plus 4 over alpha squared plus 4 and over alpha squared plus 4. And all of this is our y alpha. Now if we take the inverse Laplace of each side, we'll be left with y of t on the left and what y of t is equal to in terms of t, a, b, and g on the right. So taking a look over here at our sheet, right off the bat, we should be able to figure out some easy transforms for these two functions here, since we know that the inverse Laplace transform of alpha over alpha squared plus 4 is just, so I'm factoring out an a here, that the inverse Laplace transform of alpha over alpha squared plus 4 is just a times cosine of 2t. We can deal with that relatively easy. So I'm gonna actually put y of t over here and start adding components to it as we take components off on the other side. So we have a cosine 2t. That has been dealt with. Now we have this term over here, and it looks like, let's factor this b out, the Laplace, the inverse Laplace of b times 1 over alpha squared plus 4 is almost in a form that we can deal with very easily. If we divide b by 2 and multiply by 2 up here, this is looking a lot better because we know that the Laplace transform of sine of 2t will give us 2 over alpha squared plus 4. And as a result, since b over 2 is just a constant, we can bring that out here, and this is just b over 2 sine 2t. And that is all done. So the last one we have to deal with here is capital G of alpha over alpha squared plus 4. We can rewrite this as g of alpha over 2 times 2 over alpha squared plus 4. And we know the inverse Laplace transforms of both of these. So we can use this rule here that f of s, so the Laplace transformed version of f of t, and g of s, the Laplace transformed version of g of t, the inverse Laplace of both of those multiplied together is this. Let's see. We're solving the inverse Laplace of g, capital G, of alpha over 2 times 2 over alpha squared plus 4. This will be the integral from 0 to t of f of t minus tau. Well, that means take the inverse Laplace transform of f of s and replace all of the t's with t minus tau. So this, we already saw a second ago, is just sine of 2t. So we say sine of 2, but instead of just t, we have t minus tau, like that. And then g of tau dt, because remember, we don't actually know what this function g of t is. We have to kind of leave it in this form, which is good because I don't particularly want to evaluate any integrals right now. So we are left with, if I go put everything together, there we go, we're left with a cosine 2t. We see that in 4 of our options, plus b over 2 sine of 2t, that's everywhere else as well. And then c matches everything else. So 15, whoops. So I said 15 should be c. No, 15 is b. I have to be very careful here. I was not careful enough. We lost our factor of 1/2 that was sitting on our g of alpha. So we need that 1/2, and b is our correct answer. Gotta be careful. 16, the function y of t solves this initial value problem. I need to go grab our little chart here. So just like we did for our initial value problem up here, we are replacing all of our y primes and our y's and also our right-hand side with their Laplace transform, their corresponding Laplace transforms. So y double prime will be alpha squared y of alpha minus alpha y of 0, which is just 0, minus y prime of 0, which is also 0. And then we're adding 2 alpha y of alpha, and then another initial condition that we, again, can't use, plus 5 y alpha is equal to gamma of t minus 7. And yet again, I keep forgetting to Google this, whether or not this is actually gamma. I sincerely hope that I'm saying the correct. That would be hilarious. I'd hate that. Okay, we see that the Laplace transform of gamma of t minus c is e to the negative cs. So we get e to the negative 7 alpha. We can factor this side over here, y alpha times this quantity is equal to e to the negative 7 alpha. We can divide this out like, whoops, like so. It's a little messy over here. Plus 2 alpha plus 5, just condensing things a little bit, to y alpha. Okay, let's rewrite our denominator and see if we can make something happen. So we see that y of alpha is equal to e to the negative 7 alpha times 1 over alpha plus 1 quantity squared, so that will give us alpha squared plus 2 alpha plus 1 plus 4. So at this point, we are ready to find our f of t, which is the inverse Laplace transform of, did I say f of t? Y of t, which is the inverse Laplace transform of y alpha. And at this point, we know how to take this inverse Laplace transform. We know that the inverse Laplace transform of e to the negative cs multiplied by the Laplace transform of f of t, which we know how to find here, is uc of t times that function t, but we're replacing all of our t's with t's minus c. So let's kind of explain what's going on here a little bit. We have our 1/2 factor here. This e to the negative 7 alpha will help us find the first bit. We see that that's uc of t, so u7 of t in this case. And then we have this function here, whose inverse Laplace transform is going from here to here. So we have b, which in our case is 2, and a, which in our case is negative 1. So we can multiply by e to the negative t sine of 2t. But what did I say? We have to replace all of our t's with t minus c, where c is this value that is subtracted in this exponential and ends up as the u of c term down there. So we're going to have negative t minus 7 and 2 t minus 7. And with that, we have ourselves, missing a parentheses over here, we have ourselves our solution, and they want our solution for t greater than or equal to 7. And because u7 of t is the unit step function which activates at 7, after 7, u of 7 will just be 1. So we're left with 1/7 e to the negative t minus 7 sine 2 t minus 7. So 16 is A. Let's find the Laplace transform of this guy. We're going to be practicing, making a function out of unit step functions, which is a little bit weird to kind of wrap your head around, but it's kind of cool in the end. So we're going to work our way down. When the function is less than pi, we want everything to be equal to, we want our function f of t to evaluate to 0. Between pi and 2 pi, we want our function to be equal to t minus 2 pi, and then we want it to go back down to 0. So we know that we want a term that is, that's mu. I want u pi of t multiplied by t minus 2 pi. And let's see, this is f of t. Because when t is greater than pi, we know that we want this to be happening here. And this also fulfills our first case, because this u pi of t will not be equal to 1 until t is equal to 1. And now really all we have to do is add in u2 pi of t times t minus 2 pi, so that when pi is greater than 2 pi, this is equal to 1, this is equal to 1, and so everything evaluates to the 0 that we're looking for. Okay, cutting a bunch of that stuff that I just did out that was a little bit incorrect in a very important way, we are going to split up our equation here a little bit. So we have f of t, fancier f this time, is equal to u pi of t times t minus pi, and then we're going to, we've taken a pi out of here, so we need a minus pi u pi of t minus u at 2 pi of t times t minus 2 pi. And see, what we've done here is put both of these unit step function equation sections into forms that we are much happier with to do our Laplace transforms. Because if we head on down here, we see that uc of t times some function of t minus c, where that minus c value is the same as the c that's in the uc of t, we have a nice little way to solve this. This will just be e to the minus cs times the Laplace transform of this original function, f of t minus c, but we replace all of the, we disregard all of the c's. So we can deal with that. We have f of alpha. We're going to start building this one up, dealing with our first term first. We said that uc of t is going to, trying to read tiny font, going to contribute to e to the negative cs, so e to the negative pi alpha multiplied by the Laplace transform of this guy disregarding the negative pi. So doing so, the Laplace transform of t is s squared, so I write alpha squared. For our next term, we just have a constant multiplied by u pi of t, and u pi of t is going to become e to the negative pi alpha over alpha. So negative pi e to the negative pi alpha over alpha. And then for this last term, it's very similar to the one that we did to begin with. We will end up with minus e to the negative 2 pi alpha from this c value here, and then the Laplace transform of this disregarding the 2 pi because it's equal to this c out here, which gives us another alpha squared on the bottom. And we should be done here. If we take a look at option A, if we look at option A, yep, A matches ours exactly. So 17 is in fact A. I gotta say, this kind of stuff is a little annoying when you're trying to learn these, all these rules, whatever. But when you're putting them into practice and everything falls into place, and you look back and you're like, wow, that was pretty cool. That's a cool feeling, I think. 18, we have a real 2x2 matrix A with one eigenvalue and a corresponding eigenvector, and we are trying to find the solution, the general solution. So we can take V1, so 1 and 2i, e to the lambda 1t, so 3t plus 2it. We can split this up into e to the 2ti. And we can do a little bit more to this. Let's take this e to the 2it and replace it with, what's making that noise? E to the cosine 2t plus I sine 2t. And from this, we can figure out what our real portion of our solution will be, our imaginary portion of our solution will be, and then we can slap a C1 and a C2 on it and call it a day. So finding our real solution, that's going to come when we multiply cosine into the top and sine into the bottom. That gives us cosine 2t, I'll put the C1 out here, times negative 2 sine 2t, because I times I will give us negative 1, e to the 3t plus c2 times the imaginary portion, which we will get when we multiply sine on the top and cosine on the bottom. So sine 2t, remember we drop the I, and then 2 cosine 2t e to the 3t. And that should be it. Yep, C is looking good to me, and the answer key agrees. 19. In the phase portrait of this system of x prime equals ax, for that a right there, the origin is what? So the behavior of the origin is determined by the signs and the properties of our eigenvalues in general. So let's solve for our eigenvalues. We're solving the determinant of a minus lambda I equals 0. That gives us negative 3 minus lambda times negative 1 minus lambda plus 2 is equal to 0, or lambda squared plus 4 lambda plus 5 is equal to 0. How will this factor? Well, it's not looking like it's going to factor normally, so let's apply our quadratic formula. Negative b over 2a will give us negative 4 over 2, so negative 2 plus or minus the square root of b squared minus 4ac, that'll give us negative 4 over 2. This is 2i, so I. And because we have a negative real part of our eigenvalues and an imaginary part at all, that means that we're going to have spiraling behavior in towards the origin because our eigenvalues are negative. So as t approaches infinity, anything that's multiplied by e to that negative 2t value will tend towards 0. So we get an asymptotically stable spiral point because things are stably spiraling in towards that origin as time goes on. Nothing is escaping per se. Okay, 20, we have a matrix with some eigenvalues and some corresponding eigenvectors. And we are trying to solve this initial value problem of a non-homogeneous system of differential equations. So the reason that they give us the eigenvalues and eigenvectors is so that we don't have to do the work for ourselves to see that e to the 2t, or some constant times e to the 2t, is not overlapping some of the solutions that we get for our characteristic equation, or for our homogeneous case of this system. So a safe guess for x particular is a e to the 2t and b e to the 2t. That transition does not work. X prime pg will be 2a e to the 2t, 2b e to the 2t. And we can plug these guys in and get ourselves a solution, at least for xp. One thing to note here is that we will have an e to the 2t in every single part of this equation here. We will have it in x prime, we'll have it in x, and we already have it here. So I'm going to plug things in as if e to the 2t was already divided out, and it'll simplify things a little bit. So we have x prime, that's 2a, 2b is equal to 2, 3, negative 1, negative 2 times x, which is just ab, and then dividing out our e to the 2t's here, we have 1 and negative 2, and this is added here. We can expand this into two smaller equations that will be easier to deal with. This is 2a is equal to 2a minus b plus 1. This will simplify down to b equals 1, and 2b, which we know to be just equal to 2, is equal to 3a minus 2b, so minus 2, minus 2. So we have negative 4 on this side. We can add that over. That's 6 over here. So a is equal to 2. We can go replace our a and b here with 2 and 1 for our solution to xp, and we're ready to form x of t and get all of this over with. This is c1, 1, 1 e to the t plus c2, 1, 3 e to the negative t plus 2, 1 e to the 2t. Using our initial condition here, x at 0 is 4, 5. We can set up 4, 5 equals c1, 1, 1 plus c2, 1, 3 plus 2, 1. Subtracting this 2, 1, we will get 2, 4 over there, and we can set this up as an augmented matrix to solve. 1, 1, 2, 1, 3, 4. Subtracting row 1 from row 2, 0, 2, 2, simplify to 1, 1, subtract, and we see that c1 is 1 and c2 is also 1. And what the question is asking is, what is x1 of t? Well, x1 of t is just this top line here of coefficients. So that's e to the t plus e to the negative t plus 2 e to the 2t, which is not d, I missed. It's, it's not e, it's d. And answer key agrees. This was a pretty painful test for me. I hope it comes out better after we edit it. And by we, I mean me.